Cool. I thought the other talk sounded way cooler than this one, so thanks for being here. All right. As Willie said, I'm Kevin, and I come from way over here. I'm American, but I live over here, yeah, in this, as he said, this tiny small town called Seoul, and there's like 1 or 2 other people that live there as well. So I work for a company called Skelter Labs. We're hiring if you want to come to Seoul. And ironically, we actually just moved offices to Gangnam, which puts me 1 step closer to my life goal of being this guy. So today we're going to talk about protocols. So protocols are an Elixir feature that I think is really cool, and it's kind of built into some of the core parts of the language, but it's also something that not a lot of people talk about, and something that I didn't really discover until later in my journey through Elixir. And so we're going to kind of go through the reasons why Elixir protocols exist and talk through some practical use cases of how you can use them. So to first go through what protocols are, I first want to talk about why protocols are. So why do these exist? So to go through that, we need to understand that programs, all programs regardless of the language, are made up of 2 elements, 2 fundamental elements. And those are types and functions. So types are the data of our system, the nouns, the strings and the lists and all the stuff that makes up the data. And then functions are the operations on that data. They take data in, they transform it, they do stuff to data. So we have strings, and strings can be split, and we have lists, and they can be flattened, and maps can be merged, and structs can do what they want. So, so these are kind of the core fundamental things that all programs everywhere are made of. And so languages, all languages, try to organize these things in the most optimal way possible. So how can we organize functions and organize data in a way that makes the most sense for everyone? But when doing this, there's a problem that arises, and that problem is called the expression problem. And so we're going to walk through today a little bit about what the expression problem is, and why languages get tripped up on this thing, and what we can do to fix it. So what the expression problem says is how can we add new types, so new types of data to our systems, and how can we add new functions to our systems without modifying the ones that we already have? So without modifying our existing types, without modifying our existing functions. So to explain this, I'm going to walk through kind of a simple example. We're going to use a couple of very simple types representing shapes, and we're going to talk about functions that can apply to these shapes, so calculating area and perimeter, for example. So first, let's try an imperative style, so like an object-oriented style. So these examples are going to be in Ruby, but if you're familiar with Java or JavaScript or PHP, this should make sense. OK, so here we have a class. Can you guys read that OK? Maybe. So here we have a class. It's a rectangle. It has a couple of instance variables for width and height. And when we call area, it's just going to calculate the width times the height. So pretty simple. And then we've got a super simple printer that will just print out the area when you pass it a shape or a rectangle. So question 1 of the expression problem is, can we add a new type to our system without modifying either the existing types that we have or the existing functions that operate on those types? And in an OO system, adding types is kind of like is optimized. So in this case, very simple case, yes, we can add new types to this system. We don't have to change anything, right? We can now create a circle, and it calculates its area differently, but our printer still maintains compatibility with both our existing type and our new type. So we can add a new type, and everything's cool. So new types, cool. All right, so second question is, can we change a function or implement a new function without changing anything else? And this is key because sometimes your types might not be owned by you, right? They might come from some third-party library. They might come from some other part of the system that you don't have easy access to. Or sometimes you just don't want to change more code. You just want to like do things in isolation. So if we wanted to change our printer to output the perimeter instead of the area, how could we do that? Well, that starts to put some roadblocks in our way, right? If we wanted to implement perimeter, we would probably have to go into rectangle class and into circle class and add the perimeter function. We could this is Ruby, so we could monkey patch, which is sounds like a terrible thing to do, and it usually is. And so we could do that. We could wrap our instances in some other class, like an interface, like what Java does. But there's some downsides to doing that. So no matter how you slice it, in most imperative languages, changing functions require you to change your types. And that's just kind of the way that those things are. So we'll say that adding new functions or changing functions is difficult. All right, so now let's try a functional language. And we're at ElixirConf, so let's write some Elixir code. So here we've got the same exact thing. That we've got a rectangle. It calculates the area. But this time we're going to pass an instance of this struct to our area function to calculate the area. We've got the same thing, a printer which takes a rectangle and then outputs using the rectangle module is going to output the area. And so the first question is, can we add a new type without modifying any other functions in our system? And that starts to get a little crazy, right? Because we add a circle, and now we have to update printer to know about what circle is, because it currently doesn't know how to call over to circle. So we would either have to add another print function that takes a circle and calls the circle module, or we'd have to do some pattern matching some other way, or pass a function reference, which is not optimal. So adding new types to our functional system typically requires us to change our existing functions. So not optimal. However, if we want to change our printer to print out the perimeter instead of the area, although it might not seem obvious, that's actually not that hard to do, because in functional languages, we've decoupled the data from our operations, decoupled the types from our functions. And so we can just implement the perimeter function inside of printer if we wanted to. So that might look like something like this. We could just say, all right, we know the printer knows how to calculate the perimeter for rectangle and circle, and it'll just define that itself. We don't have to change our existing types, and everything's all good. So adding new functions, cool, we can do that. All right, to recap, the expression problem. Adding new types for an imperative language typically doesn't require modifying existing functions, although adding new functions or changing functions typically requires us to change our types. And the direct opposite is true for functional. So if we want to add new types to a functional language, typically have to modify functions to handle those new types. But if we want to change just functions, we typically don't have to go change our types. All right. So this is where protocols come in. So protocols are a language feature of Elixir, and they allow us to solve this problem. So they were influenced heavily by Clojure. I'm not going to say that they were copied. You can ask Jose if he would say that. They came from Clojure, and they kind of follow the same sort of pattern that Clojure does. These are an Elixir-only feature, so this feature does not exist in the underlying Erlang system. And what a protocol does is it decouples the definition of a function from its implementation for a specific data type. So we'll walk through what that means. Basically, before, when we had our data, which went directly to a function, a protocol puts an intermediary step in between there. So we take our data type, we pass it to our protocol, and then our protocol, given the implementations that it knows about, will call a implementation for the data type that you pass it. So let's walk through a very basic example of that. Okay, so here we're going to create a protocol called blankable. And blankable just has a single function, blank, which will tell you if a data structure is blank or not blank. So if we want to, we define the protocol using the def protocol. It's actually a macro. And you can see that we defined a single function, and we only defined the head of the function. So no bodies of the function go inside of the protocol definition. But now if we want to implement our protocol for a given data type, we can now do that. And we use the def impl macro. So we say def impl blankable for, in this case, a bit string, so just a string. So we can say that a string is blank if it's an empty string, and if it's not, if it's anything else, it's not blank. All right, then we can go on and we can define implementations for our blankable protocol for other data types. So we can define them for maps, and we can say that a map is blank if its map size is equal to 0. And we can also, and I think this is kind of the key point to protocols, is that we can define implementations of our protocols for structs, so for our custom structs. So here we have a post struct, which has a title and a body attribute. And we will define, define an implementation of the blankable protocol. And because we've defined it inside of our struct module, that's just kind of a shorthand thing there. And so we can say that a post is blank if its body is nil, and otherwise it's not blank. OK, so now that we've defined our protocol, blankable, and we've defined some implementations of that protocol, let's see how we can use it. All right, so the first one, we'll say, so we call a protocol by calling the protocol function. So we blankable.blank, we'll pass it the string foo. And that is going to call the string implementation of our blankable protocol. So it's going to call that implementation for string, and we'll get false. And we can now call the blankable protocol for a map. And this will call the map implementation. And we can also call that for our post struct, and that will call the implementation down here. And so we get kind of different implementations that get called based on the data type that we pass it. And we can also, if we pass something that we have not defined an implementation for, we'll get an error. So in this case, we're passing the atom foo, and we'll get the error, protocol blankable is not implemented for the atom foo. OK, so to diagram this out a little bit, we have our blankable protocol, and we have implementations. So we have one for a bit string, and for a map, and for a post. And if we pass a string to our protocol, it will dispatch to the string implementation. If we pass a map, it will dispatch to the map implementation. And if we pass a post, it will call the post implementation. All right, so the last thing I want to talk through kind of in the introduction to protocols here is the ability for us to define a default implementation. So if we don't want to implement for all types, we can say we want to implement this for what's called the any type. So here you'll see that we've updated our def protocol module, and we've said we've added this fallback to any attribute. So if we set that to true, and then we create an implementation, and we use this any keyword. This will say, if you pass me any type that I don't have a specific implementation for, use this implementation. So now, if we call our blank with the atom foo, it will call the any implementation, and we'll get false. The other way that we can do this is by not doing the fallback to any, but we can use the derive syntax. So we've got our post module, which is a struct like before, and instead of defining our implementation, we can say @derive blankable, and that says use the default implementation of the blankable protocol for this struct. So it's kind of a shortcut, especially if you're defining lots of structs and you want the same behavior for each one, you can use this, so you don't have to type it out in each one. Okay, so there we go. So blankable.blank for post is going to call the any implementation. All right, so now that we're experts in protocols, let's go back to the expression problem. So recall that before, in a functional language, we were able to change functions, able to add new functions without modifying our types. But if we added a new type, we had to go change our existing functions. So this time, instead of calculating the area as just a function, we're going to use a protocol. So we'll define a protocol here called area, and it has a single calc function there. And then our rectangle is, instead of just defining an area function, is going to define an implementation for the area protocol. So this defines the area that way, but no code here is changed. We've just inserted our protocol layer between our data type and our function, our implementation. Okay, printer, and the printer now is going to use the area protocol to print out the area. And so, the question of the day is, now that we've converted this to using protocols, can we add a new type of shape without modifying our existing functions? And the answer is, we totally can, because now we can create a circle. Our circle implements the area protocol, and it can be passed to the printer. The printer calls the area protocol, and we've kind of done like a polymorphic thing here. And so we've totally solved the expression problem for functional language. Like, that's awesome. Yeah. All right. And furthermore, we can also, let's say that the printer wanted to implement wanted to now call perimeter instead of area. Well, it could define its own protocol for perimeter, and it could just define two implementations. I ran out of code there, or room there on my slides, but it could define its own perimeter protocol, implement it for the rectangle and the circle type, and kind of do the same thing. So we have solved the expression problem using protocols. All right, awesome. Okay, so now that we know kind of why protocols exist, what problem they solve, let's walk through some of the core protocols that exist in the Elixir language. So this is protocols that ship with Elixir that you can implement for doing different things. So the first one is a pretty simple one. It's called string.cars. And this is responsible for converting a data type, or converting a data structure into a string. And Elixir implements this for like atoms and for a few other things. So we can just use this way. So if you implement string.cars for your data structure, you can like customize the way that it prints out as a string. And you can see we can pass, we can use the toString method. This also gets called whenever you do string interpolation. It's going to call the string.cars protocol. And so yeah, toString. The second one is called collectible. And this is a protocol used for taking values out of a collection. And to implement this protocol, you would just implement an into function for your data type. And it's used by the enum into function, if you've ever used that. And it lets you convert list-like structures from one to another. So in this case, we're converting a keyword list into a map. And so that's using the collectible protocol. And you can have custom behavior if you wanted to do something special for your data types. All right, the next one, inspect. So this is similar to toString, similar to string.cars, but it takes a data structure and converts it into kind of like a pretty printed format. It lets you do evals on it, and it's called like an algebraic document, whatever that means. All right, so we can inspect something, and it'll print us out a string of that. All right, so the next one is IEXinfo. This is the protocol that gets used by the I helper. So if you're in an IEX session and you say I and pass it some data type, it will tell you some information about it. So in this case, we say the atom foo. It'll say that it's an atom, that it references these modules, and it'll tell you what protocols it implements. And you can define your custom implementation of this if you want to. And the last one is the enumerable protocol. So I think this is like one of the coolest protocols. And it's used by the enum and stream functions, so those modules that iterate over things. And to implement the enumerable protocol for your own data type, all you have to do is implement these three functions: count, member, and reduce. And this will let you have your custom data type interact with all of the enum and stream functions. And so there's actually some really cool use cases here, right? You could imagine like you could have a process that keeps track of some list of things. And so you want to be able to call into your process and pull out elements of this list. You could do that by implementing the enumerable protocol. Yeah, so it lets you do map and reduce and all that stuff. Okay, so now that we've talked about some protocols in the core language, let's talk about some protocols in the wild, in libraries that are out there. So the first one I'm going to talk about is a library that you've probably all used if you've done much Elixir at all. This is called the Poison library. So this is what converts Elixir data structures into JSON and takes strings of JSON and converts it back into Elixir data structures. It's used by Phoenix and pretty much everything that does JSON encoding. So Poison implements two protocols, one called encoder and one called decoder. One encodes into JSON, one decodes from JSON. And the way that it works, so if we have here, we have like Poison encode, and we can give it some data, and it'll just print out a JSON representation of that. And the Poison encoder protocol looks like this. So we have def protocol, Poison encoder. It's got the fallback to anything, and it encodes a value. All right, and if we look, this is a little bit simplified from the actual source code, but pretty close. So we have a Poison encoder for atoms, and we can say if you pass an atom, it will, so if you pass null, it's going to print out null. If you pass true, true, false, and anything else, it's just going to toString, because in JavaScript we don't have symbols or atoms, so it just converts it to a string. But the cool part here is that you can define your own implementation for the encoder protocol and do special encoding for your types. So here we have a person with a name and an age, and instead of doing the default behavior, which would be to like create an object with a name and an age, we're just going to say convert this to a string of name and in parentheses age. So that might be something that you want to do. You want to say, anytime I want to convert this type into JSON, I want to like have some custom behavior there. All right, so the next one we'll talk about is a library called Scrivener. I think that's how you pronounce it. And this library does pagination. So pagination is a very common problem that we have when building like web apps and things. So the way that Scrivener works is it works by default with Ecto, and it will handle paginating a query based on some input parameters. So in this case, we can say my repo paginate this user Ecto struct, and we want to say with page size of 10. And then this will return us a Scrivener page structure, which has the entries that we requested plus a bunch of data about the page size, like total pages, total records, all that stuff. And so Scrivener implements or defines a protocol called the Scrivener paginator. And this has a single function called paginate, and so the implementation that it ships with is for an Ecto query. So here we have a paginator implementation for Ecto query. It takes anything that's an Ecto query plus our page size config values, and then it just does the limiting and offset of our ecto query and returns the structure you saw up the top. So this is all cool, but what if we wanted to implement, like, let's say a cache? We wanted to like cache our records in some process. Well, we could totally define our own paginator for like our custom types. So we could say like, I want to define an implementation of the Scrivener paginator for like my thing, maybe some cache process or something like that. And this could implement the same function here. And now the cool part about this is that whatever you're passing this to, like the front end, it sees the same thing, right? It sees a Scrivener page with entries, and it doesn't care whether you got them from ecto or you got them from the cache. It's all like the same thing. So that's kind of a cool thing, I thought, for implementing a protocol. All right, so let's walk through kind of another use case that you might commonly see if you're writing any application. This is like integrating with some third party. So you want to talk to Twitter, or you want to talk to GitHub, or you want to talk to something. You could actually solve this problem using a protocol. So let's say that we want to, let's say that we have an API that we want to send messages to, so GitHub or Twitter or something. So we have a message. In this case, we want to fetch users, so fetch user message, and we're going to say with the roles of admins, and we're going to send it to our API. So API, send this message. So we could implement this using a protocol. So we could say, I'm going to define a protocol called API message, and we'll define two functions on there. One to build the request, so build some HTTP request to go fetch users or whatever, and another function to parse the response that we get back from this API. And so this might be what our API module looks like. So we have our send message, which calls into the API message, build request, and then does some HTTP stuff, and then calls back into the protocol to parse the response. And if we look at this implementation for our fetch user message, this is a struct with a role, and then it does building the request body and parsing the response. Now the point that I want to make here is that send message function there could do a whole bunch of logic that is universal to all messages. So it could do like some authentication, it could do parsing to and from JSON, or it could do like cookie handling, like anything that was universal to all messages. And then your message types have a very specific implementation. Just build the request that is specific for this message and parse the response that is specific to this message. And we can add like tons of messages and never have to change the underlying logic that's universal there. All right. So the last, or a few things that I want to talk about, this is a question that I often see on forums is, should I use a protocol or should I use a behavior? And the question that I've sort of learned to ask myself is, can each implementation of my function take the same data type? And if the answer is yes, I can distill this problem down into a single data type. Then I might choose a behavior over a protocol, because a protocol is specific to different data being passed to my functions. So let's look at an example where you might want to use a behavior instead of a protocol. And a behavior, by the way, for those who might not know, behavior is just a way to define a specification for a module that says this module needs to implement these functions in order to implement this behavior. And it doesn't say anything about data. It's strictly about functions. OK, so let's say that we want to write a library to send emails. So here we've got a message, and it's got a to and a subject and a body, like standard things you would have with an email. And we want to have a mailer that's going to deliver our message. Now, we might come across the use case of where we want to change the way that we send our messages based on like whether we're in production or we're in test environment. So we might want to send using SMTP in production, but use some like cache thing in testing so that we can assert on messages. So you might think like, well, I could implement a protocol for this, right? I want to change the behavior based on something. But the actual reality here is that our data, which is that first line, that message, that thing stays the same across each implementation, right? Whether we're sending through SMTP or sending through some cache or sending through Mailgun, like the message data is always the same. The to, the from, the body, the message, like that all stays the same. So a protocol would probably be better here. A behavior would probably be better here than a protocol. So in this case, our mailer will like get the current adapter depending on like what config, whether it's in production or whatever. And it'll deliver that message, and then we can define different implementations of our adapters that each take the same message data structure. So we can define an SMTP adapter, a SendGrid adapter, and a test adapter. So the rule of thumb there, if your functions can take the same data type, use a behavior. If you need your functions to take different data for each implementation, then lean towards a protocol. All right, the last thing I'll say here is don't get too carried away. When I first dove into protocols, I was like, oh yeah, let's use protocols for everything. And that's not usually optimal because they do add a little bit of layer of indirection there. So just be a little careful. And think of this as just another tool in your toolbox, right? It's something that solves a very specific problem, I think, in a very, very elegant way. And so if you find yourself coming across these issues where you need to have different data types that can be kind of changed dynamically the functions that they're calling, then protocols might be pretty good. So with that, yeah, 고맙습니다. Thank you.